This is what I want everybody doing anytime there's a moderation. So researcher interested in studying the relationship between age and endurance, particularly how this relationship may depend on the amount of exercise per week that someone participates in. Their data are centered. So quick catch up, we're walking through, whenever we do moderation, we're gonna follow, oh, great. So the first thing we're gonna do is we're gonna draw the theoretical, not the statistical model. Why did I choose to draw the theoretical model and not the statistical model? Because the theoretical model is what I think is happening. The statistical model is what's happening mathematically under the hood, but it doesn't really do a lot to help me tell the story. The theoretical model, which looks like this, helps me understand, oh, there's an existing relationship between age and exercise, or age and endurance. And then I think that that relationship might depend on, as in it might change as exercise changes. Yeah.
Since we're getting into the weeds, does it matter if exercise is above or below?
It does not. So if you drew, that is the one exception. Thank you. If you drew it exercise down here with it moderating that way, and I think I saw you do this like that, that's fine. Identical conceptually. And then, whoops. And then there is also a relationship between exercise and endurance. Lisa says yes, but ask her to explain why. Wait, M's question or something else? Kearns, just unmute and tell me. You can do it.
I was trying to unmute Alice's question. Alice is asking about the dashed line and why it's where it is.
Why it's dashed?
Yes.
Yeah, so it doesn't have to be. There's another one. If you drew it solid, that's fine.
So if we drew and then
if you drew it like that, that's fine too. Sometimes I draw it dashed because sometimes people draw their theoretical models without that line because they don't care about that relationship. But for our purposes, I want us to always draw that line. You don't need to draw it dashed. You can draw it solid. That's totally fine.
Would
Jess?
the middle line be the line between exercise and age and endurance be dashed?
Nope, they're all relationships. Yeah, sorry if the dash confused you. I just meant that like sometimes people, that's not a primary relationship of interest, but for our intents and purposes, if it makes things easier, just draw lines. We'll make it easier. Just 3 lines.
Jess?
Yeah.
After you do this one, if we have time, could you draw it as if exercise was categorical?
And there were 3 levels? Of
Yeah,
course.
thank you.
Yep, good. So now I want you to notice something. You have 3 lines. Yes? Everyone have 3 lines? How many slopes or coefficients are there in your coefficient table? How many? 3. There's an intercept and 3 slopes or 3 other coefficients. Other than the intercept, which is a number, there are 3 coefficients. The number of coefficients in your table must always match the number of arrows in your theoretical model, your drawing, because each one of those lines is representing a coefficient. So now we should be able to label them. So step 1, draw the model. Step 2, label the model. What is the relationship between age and endurance? Negative 0.24. And I'm going to indicate whether it's significant or not. It's significant. I can literally just go down the line. Yep. What's my next relationship? Exercise to endurance. So that's up here. 0.43 p less than 0.001. We want to write the p's out. We can do that too. We got room here. So you got to draw your model big enough. You can't draw it teeny, so you don't have room to label the betas. You got to draw it big enough. Okay. P 0.001. Last relationship, only 1 line left. That's going to go here. 0.21 p less than 0.001. It's not pointing at an outcome, which is a reminder that it's not a slope. It's pointing at a slope, which reminds us that it's a change in slope. This thing here is going to come in and bump this here. So now, before we get there, we have everything we need in this drawing already to tell us what's going to happen between age and endurance when exercise is average, low, or high. So I'm going to take these boxes out because they get ugly. Negative 0.24, p less than 0.001, negative positive 0.21, p less than 0.001. In order for the relationship between age and endurance to be that, what would have to be true about exercise, like visually? What would have to happen to this line? Yeah, let me just think aloud. The way I think about it is that in order for age and endurance to have a relationship of negative 0.24, this arrow can't hit it. That arrow cannot hit it. If it hits it, it's gonna change. The only way for that arrow to not hit it is if this is 0. And what is 0 when we center? Average. So the only way that the relationship between age and endurance can be negative 0.24 is when exercise is what? Average. Yeah.
Since R doesn't know which way our moderation is working, would that 0.21 apply if the arrow was pointing to the exercise endurance line? So if I had low, middle, and high age, would you change the relationship be the same?
Yeah, but this would be the starting relationship.
Yeah, but those numbers would be the same?
This moderation term would be the same. Yes, but it would be 0.43 would be your answer to the yeah. Now, so 0.24 and negative 0.24 is our starting relationship. It's like if I erase the top half of the model. It's the undisturbed slope you can think about between age and endurance. It's literally like if I erased everything above that one main effect line. Now, if exercise goes up, it's gonna come into that negative 0.24 and it's gonna hit it, and it's gonna hit it by that much. So there's where it started, and it's gonna hit it by that much. So we're left with negative 0.03. And what happens if exercise goes down?
Minus 0.21.
Yep, minus 0.21. That change in slope is always what happens when the moderator goes up by 1 standard deviation, not down. So if it goes down, you just reverse the direction. Okay, that's it. Do that before you do anything else. That tells you what all of these lines are. That tells you what happens to age and endurance as exercise goes up. First of all, what happens to endurance when age goes up? It goes down. As you get older, your endurance goes down. Make sense? But what happens when you exercise a lot? It buffers it. It makes that effect far less pronounced. What happens when exercise is low? It makes that effect even more pronounced. Good. There was a question. Yeah.
Yeah, just for clarification, I got 0.03 as when exercise is high, and then you explained.
Oh, sorry. I did it high.
Yeah,
I just
okay.
did it. Yeah, I'm
Sorry,
sorry.
I messed
Yeah, I can switch them. I did it. I just did high. I'd always do high first. I don't know why I listed low first. Here, I'll switch it here.
Hey, Jess.
Yep.
So then if we're reporting like or interpreting that line for when exercise is high, because the p-value on that line is
Hold on, I'm not there yet. Hold on. Yeah. So minus 0.24 plus 0.21 equals minus 0.03. So now we have our 3 slopes. So draw the model, label it with the coefficients. The number of coefficients you have should match the number of lines you have. The same is true when you have a categorical, and I'll show you in a second. Then figure out, the next step is to figure out, really, I would even skip the equations first. You could do the equations next, but I would skip and do, so then what's my relationship between my predictor and my outcome as if my moderator doesn't exist, meaning it's average? What happens when my moderator is high, and what happens when my moderator is low? If I look at my graph, I can say, well, I know when it's average, it's negative 0.24. When it's high, it's negative 0.03. And when it's low, it's negative 0.45. Now we have to look at the simple slope results. We've got 3 simple slopes here, and we have p-values. So first p-value is 0.531. What does that mean about that line? It's not significantly different from 0. The null hypothesis is that B or beta is equal to 0. So you know what I'm going to do on this graph? I'm going to write flat. Now this one's not that bad because it kind of looks flat, but it doesn't always look flat, and it still is sometimes. So anytime I see that simple slope that's not significant, I'm going to write flat to remind myself that line is not significantly different from 0. Now, when exercise is average, there's a negative relationship between age and endurance. It's significant. When exercise is low, there's an even steeper and significant relationship between age and endurance. So now what's the story? In general, there's a negative relationship between age and endurance. But when people exercise a lot, that relationship what? Goes away, disappears. Good. Yeah.
Why would
the p-value be less?
I mean, well, yeah, why would the steeper slope have a higher
Could be error.
value? It could just be.
Just like error, noise. Yeah. Yep.
On the relationship between age and exercise, is it the relationship between age and endurance when exercise?
Sorry, age and endurance. Yeah. Relationship between age and endurance. So the relationship between age and endurance is negative. As age goes up, your endurance goes down. However, when you exercise a lot, that relationship goes away. So you could say it buffers it. You could say it makes it go away. You could say that relationship disappears when exercise is high. Yeah. Yeah.
When you were talking about the relationship between age and endurance when exercise is above low and high, there's also a constant that happens as a result of that moderator. Does that not affect the relationship? So like when I look at the formula and kind of plug those numbers in, there's a,
The intercept?
yeah,
Nope.
that doesn't impact the overall.
No, that impacts a very specific, so now let's do that part. So now let's do the equation. Because I think what's happening is people are like, I gotta do the equation, but they're not necessarily thinking about like, what is that equation for and when is it helpful? The equation is not particularly helpful for understanding the complete moderation or the slopes. The theoretical model and the graphs are much more helpful for understanding that. And quite frankly, and the simple slopes analysis, and quite frankly, that is more important. The equation is helpful for predicting a particular value. What I wanted you to understand was the connection between the equation, the model, and the table, because those are all just models. They're the same model. We're just translating from one form to the other, but you can work in the form of the model that is most intuitive to you. And for most people here, it's not going to be the equation. For some of you, it might be. If you are like, I love the equation, it really helps me understand the moderation. Great. But if that's not you, don't go to the equation first. Like that's not going to be the thing that helps you understand what's going on. And understanding what's going on is far more important than generating an equation just to generate an equation. So if we want to generate the equation though, all we have to do is here are our B's, here are our betas. You just go down the coefficients. So y equals 25.89 minus 0.26 age plus 0.97 exercise plus 0.05. I'm just going to call it moderation. Here it's y equal no intercept, nothing, negative 0.24 age plus 0.43 exercise plus 0.21 moderation. All this indicates what you're asking is if we plug in one standard deviation above the mean here, it just means that when age is average here, when age is centered average, that people who are higher in exercise are going to start 0.43 standard deviations higher in endurance than people who are low or average in exercise. That's all that means.
That's where they start, but it's not the relationship.
Correct. The intercept is not the relationship. The intercept is the predicted score on the outcome when your predictor is when all things are 0, but in this case, 0 is always centered, so average. Yeah.
Can we find the point with which our line loses significance? Like if I was an exercise physiologist and I said, if you exercise 3 hours a week, you reverse the effects of it.
You're not reversing it.
Or you stop the effects of it.
Yeah, I get what you're saying. You would need more data and you'd probably need a non-cross-sectional survey.
Can you find, like statistically, can you find the point with which it loses?
Yes, but not with linear regression. Yeah. So the issue is what you're talking about is a point, like in a linear regression, by definition, you have a line that's going up in perpetuity. What you're talking about is a point where that line goes like this. So yes, you can use growth curve modeling. You can use alternative forms of analysis to model non-linear relationships that get flat eventually, or parabolic that actually come down because maybe when you're 90, you shouldn't exercise that much. I don't know what the relationship would be, but yes, but not with linear regression.
So is moderation then like steps, it's like in between linear regression, is that and more advanced? It's only like some steps, because then the lines then aren't linear, or the relationship then isn't linear, the relationship is always changing.
I don't know that I would place it there categorically. Like, I don't know, I would say it's in between those two. I would say that it's a good like caveat. Yeah.
Were you talking about the change in the slope to where now the slope is effectively zero?
No, just in terms of like calling it
Like a ceiling.
a like fully linear relationship, if the, like, you're looking at it at different points in time or inputs, it's different, so it's not like along a line. And
Or the idea that like, well, I can, like, is the idea like, can I always erase that relationship if I just keep exercising more? And the reality is probably not in perpetuity. Yeah, yes, yes.
So for the flat line, you're saying it's not significant. The wording, are you always just gonna say the relationship is like on, or like say, cause I was thinking like, oh, there's no significant effect on the relationship.
No.
Is that correct? Or do you have to say like, there's no relationship?
There's no, if you're gonna say there's no effect, let me show you what it's actually testing. So it was when exercise was high. So relationship between age and endurance when exercise is high. So you have age and endurance. That's the relationship you're testing. What type of test? It's a t-test. You know it's a t-test because that's the hypothesis test that gets tested when we test coefficients. The null hypothesis is that the slope is zero, that this slope is zero. The alternative hypothesis to that t-test is that slope is something other than zero. Based on the number of people in your study, so your sample size, you get a t critical value. Then based on your actual beta, which we know was negative 0.03, what we got, you get a t calculated value. Then you determine, is that t calculated value in my rejection region of my null curve or not? In this case, it wasn't. So we retained the null, which is that B or beta is actually not different than zero. So it's actually zero. So you can either say there's no relationship, or if you want to use the word effect, you would say when exercise is high, age has no effect on endurance. Not that the relationship has no effect, because what would the relationship be having an effect on? There's nothing. The relationship is the relationship. So there's only age and endurance. Age is having some effect on endurance. When we retain the null hypothesis, we're saying age does not have an effect on endurance. That's broken. Make sense? Cool. Any other questions?
I have a question on that note.
Yeah.
Because that sounds kind of causal. Should we like couch it in like there's no longer an association with that?
Yes, that's
Okay,
better.
okay.
You guys are good at that. You guys are good at catching me on that. Yeah. There's no longer an association between age and endurance.
Thanks.
Yeah.
Dr. D, I have a quick question. When you write down the hypothesis, your B beta, it just means B or beta,
B and beta, they're the same thing.
but it doesn't mean B divided by beta.
No. Yeah,
Okay.
yeah, sorry.
Okay.
Yeah,
Okay.
yeah, no, B beta, B and beta. Yeah, B, remember that beta is just the standardized version of B. Yeah, it does not mean divided. Thank you.
Right.
Yeah. Alan, for sake of time, I'm going to move us to binary logistic regression, but we will have time to do one of these with categorical for sure in the review. If not, practice on your own. I'll just give you one tip for doing this categorically so that you can practice this on your own with categorical moderation, which is, let's just use the same example, so let's do age predicting endurance with exercise as your moderator, but let's say somebody made a cardinal sin and dichotomized or categorized an actually continuous variable and made it low, medium, and high exercise. So we'll make low the reference group. So that means that now you actually have in your data age, endurance, medium, exercise, high exercise, because you dummy coded, and then you have two moderator terms. So how do I draw the theoretical model in a way that allows me to label it? This is the theoretical model for like what you theorize, but this doesn't help you label it because your coefficient table is going to look like this: intercept, age, exercise, dummy code medium, dummy code high, and then it's going to be age times dummy code medium and age times dummy code high. That's what your coefficient table is gonna look like. So if I draw it like this, I have the matching problem. I've got how many arrows? 3, but I've got how many terms? 1, 2, 3, 4, 5, 6. Uh-oh, that doesn't work. So how do I draw my theoretical model when I have 3 levels of a dummy code? I'm gonna draw it like this. Age, endurance, exercise medium, exercise high. These are my 2 split moderators. You see that? Now how many arrows do I have? 1, 2, 3, 4, 5. Oops, sorry, you're not gonna have that. This is. We split. Now I can label age. I can label my direct paths. This is the D1, the D2, and I can label my age times D1 and my age times D2. That's how I would label it, Alan, if I had a categorical. If I just have a categorical with 2 levels, I don't need to do all that. I could do it just like a continuous. Solemnly swear to me that when you are practicing moderation, you will label these like this with your coefficients before you do anything else. This is how you understand what's going on. Would it be helpful if I labeled one of each of these examples with the coefficient table and threw it online? Or do we not need that? Does anybody want that?
Yes.
Great, I will do that. New topic. You're lucky we had 2 days for this. I'm glad we had 2 days for this. Last new topic of regression. So today and Thursday, we're gonna do our last new topic. Tuesday is review, Thursday is exam, crazy, spring break. Then we come back and then it's 3:18. It's wild. So today's lecture by Lo Re, Mi Fa Sol La Ti Do. Today we are going to dive into binary logistic regression. We do this in regression because it is also dealing with a single outcome, just like everything else we've done in regression. I think I told you before, the reason I don't do mediation in this class and I do it in D is because in mediation, we're actually dealing with 2 outcomes. So I leave it for D. Once upon a time, I think in maybe before my time or in my first year, there was a TA named Brendan who affectionately called it by Lo Re, and it stuck. And so by Lo Re is what you'll sometimes hear me call it. You'll hear all of us call it because binary logistic regression is just long. So binary logistic regression or by Lo Re. There are memes for this. I didn't make this up. One does not simply regress a binary outcome applying ordinary least squares. You do not. It's true. So essential question is, how do we develop regression models that predict binary outcomes? Up until this point, we've been dealing with continuous outcomes. But what happens if we want to predict binary outcomes? Win, lose, stay in an organization, leave an organization, stay in school, leave school, pass a test, fail a test, something binary. So we're going to talk about binary logistic regression. And binary logistic regression depends on kind of a totally different working mechanism, which is the idea of, we're going to go back to this idea of probability, odds and odds ratios. If you gamble, this is going to be a much easier lecture for you. I kid you not. Like, if you sports bet, you're going to feel way more comfortable with today than those of you who don't. I do not. So the first time that I learned this was the first time I learned odds and odds ratios. If you sports bet, you're going to be like, oh yeah, I know what a 3-to-1 is. So just warning you now. So what is by Lo Re or binary logistic regression? It's an alternative for multiple regression. So we're not just a mindset or mind shift here. It's a little bit tricky. We're out of moderation for now. We're not dealing with moderation. We're actually just going back to main effects only. But it's main effects that are different with a binary outcome. So I don't do this until after moderation, but we're just dealing with main effects. So some people are like, oh wait, this is actually kind of easier to some degree. Yeah, that's true. So alternative for multiple regression when our outcome is binary, but our predictors are like normal regression predictors, continuous and categorical mix of predictors. So win, loss, yes, no, guilty, innocent. For a capstone project 2 years ago, we had a student named Sean who was a jury. His job was jury selection. So he helped with interviewing jury members. He worked for a firm that worked with jury, and he used binary logistic regression in his capstone project to, based on a huge set of jury characteristics, predict jurors guilty or innocent verdicts. It's a really cool capstone. If you want to predict a categorical outcome that has more than 2 levels, then you have to use a version of this that's called multinomial regression. So same underlying mechanism. So if you understand binary logistic regression, you understand the kind of underlying workings of multinomial logistic regression. You're just predicting more than 2 categories instead of 2 categories. We're not going to do multinomial logistic regression, but it's enough to get you started.
In one of the paper I read, there's something called like.
Can you talk louder?
Oh, sorry. In one of the thing I read, there's something called like mixed effect logistic regression. Is that just binary?
No, mixed effects would have more to do with what we were talking around, like random and fixed slopes. So a mixed effect would probably be like, something's random and something's fixed.
Okay.
Yeah. Multinomial just applies to, I'm predicting something categorical that has more than 2 levels. But I think that's a really cool question because it points to the idea that you can kind of mix and match pieces of the things we've learned into different types of analyses. All right, so why do we need to do this thing called binary logistic regression? So I'm going to give you a little bit of the like under the hood of why we have to do this and not ordinary least squares. So here's regular multiple regression. So on the predictor side, we've got a mix of continuous and categorical predictors. They could be all continuous. They could be continuous and categorical. We dummy code our categorical, but we're predicting something that is continuous. In theory, all the things on the predictor side are actually what? They're all continuous because what do we do to our categorical variables? We dummy code them, and by dummy code them, we're actually making them continuous. We're forcing regression to treat them as numbers. And so we're predicting continuous outcomes. So we've got continuous on the left and continuous on the left. Yay, they match. Enter the problem of binary logistic regression. We still have continuous predictors on the right, and then we have these categorical ones we've made continuous. But if our outcome is binary, we're not predicting something continuous. What we're actually predicting is a probability of one of the outcomes. So if our outcome is stay or go, we're predicting the probability that someone would stay. That's actually what our outcome distribution looks like. It's a probability of one of those outcomes. And by predicting the probability of one, because it's only binary, you're predicting the probability of the other too. That's what makes it probability. Easy, one or the other. So the problem is, and the analogy that I like to use is like in binary logistic regression, you've got one language on one side and another language on the other side. So they're speaking to each other in completely different languages, and we have to figure out a way to get them to talk to each other in the same language. We need a translation mechanism. Now, what would happen if we didn't translate? Here we have continuous predictors on the and probability on the left. Well, how do we graph probability? When you graph actual observed probability, there are 2 outcomes. Let's say outcome A and outcome B, which is just not A. It's binary. And that's what it looks like. Yes, the observed data. So Hannah's the first person in my study and she decides to stay. So she's outcome A, right? And Priscilla's the second person and she leaves, so she's B. And I'm just plotting people on either outcome A or outcome B. If I put this in a regression model and I used ordinary least squares, R would do it for me and it would fit the best line and it would look like that. And that is not very helpful. So we're not going to do that. We have to find some sort of translation mechanism that makes the left side in the same language as the right side. Some sort of continuous number that we can predict because probability won't work that way. So enter our translation mechanism, which is called a logit. Yes, it's a very funny name, logit. What is a logit? It is a natural log of the odds. Now, it is not actually an interpretable number to the, let's call it like lay or naked eye. So it is not like I could tell you, oh, the logit is 2.7. And you can be like, whoa, that's a big logit. No, you can interpret probability. You can't interpret logits, but they're helpful as a translation mechanism. So I'm going to need you to just like go with me on the logit. And then I promise we're gonna put it back in interpretable form. Yes, I know, I promise, we'll get back there. So what does a logit allow us to do? It allows us to fit what's called a sigmoid curve. Everyone, do you guys remember like log from school and you had those curves? Yeah, sine, cosine, no, you hate that? Yeah. It looks like this. This is what a logit function looks like mapped onto binary data. This is the relationship between temperature and the probability of success. And you can see that as temperature goes up, probability of success goes down. So how do we get from probability to logits and back to probability? Because probability is what we ultimately want to predict and it's easier for us to understand. Well, let's use an example really quick. So let's use the example of the probability of being admitted into a school. So what is the binary outcome? Admitted, not admitted. But ultimately, if we have a random person, we want to be able to predict that probability of them being admitted. So probability of them being admitted is predicted by GPA plus GRE plus personal statement score. Notice that the right side is a normal linear combination of variables. Looks just like regression, but the left side is currently in a form that does not match the side. So the first thing that we're going to do is we're going to translate probability into odds. No, you don't need to understand this equation yet. I'm going to go through probability and odds in a second. So instead of saying GPA, GRE, and personal statement predict probability, we're going to say that predicts the odds, someone's odds of being admitted. And then, since a logit is the natural log of odds, that's the next step. GPA, GRE, personal statement score predicts someone's logit or natural log of odds of being admitted. Probability, odds, and natural log of odds can just be converted back and forth from one another. Just like centimeters can be converted to inches or feet, probability can be converted to odds, odds can be converted into natural log of odds, and back the other way. So I can take Jason's GPA, GRE, can't take his GRE because he doesn't have one yet. I can take his GPA, his future GRE, and his personal statement score, and I can predict his logit, his natural log of odds. Down here, and then, oh, come on, my tip broke. Yay. And then I can translate his predicted logit back up to probability. So I can say, based on his GPA, GRE, and personal statement score, here's his predicted logit, his natural log of odds. I have no idea what the hell that means because I can't interpret a logit. So I'm going to translate that logit into odds, and then I'm going to translate that odds back into probability. Oh, here's Jason's probability of being accepted. That's the underlying of how it works in terms of logits and probability. But this is the mechanism of what we're using when we run. That's the mechanism of what we're doing when we run a binary logistic regression. We're working with regular, continuous, and categorical predictors on the, and we're working with logits on the left. That's our unit of our outcome. Oh, it's because this broke.
Yeah, I think it's inside there.
All right, so probability, odds, and odds ratios, which are key to understanding binary logistic regression. I'm going to go over them, but I'm going to go over them after. So if you're like, what's the difference between probability and odds ratios and all of that? Awesome, because that's the next slide. So you have to understand, at least at like a high level, what probability, odds, and odds ratios are to understand binary logistic regression. You don't need to understand natural log of odds mathematically under the hood. We're not going there for this. I'm giving you what you need to be able to understand how to specify, interpret, and make sense of binary logistic regression models. That's how I gauge like how deep mathematically we got to go. So you do need to understand these in order to understand how to interpret the coefficients from binary logistic regression. So we're going to go through probability, odds, and odds ratio. First, just what they are. Then we're going to do a really dumb example, like a marble example, because it's helpful. Then we're going to go through a binary logistic regression model, and we're going to do probability, odds ratio again in the context of that actual example. So you'll get it 3 times. So what is probability? We remember from both 308A and probably many times before that, that probability is just the outcome of interest compared to all possible outcomes. So whatever we're interested in compared to, or divided by, if you want to be the math equivalent, all other possible outcomes. What's important here is that we're dealing with one outcome. So what's the probability that I draw a blue marble when I have a bag of a bunch of different color marbles? Odds is the probability of that same outcome happening, but compared to that same outcome not happening. So on the top is the probability that will happen, and on the bottom is the probability that it will not happen. So you're taking it in sports contests. What is the probability that the Vikings will make the playoffs? What's the probability? What are the odds that the Vikings will make the playoffs? That's the probability that they will compared to the probability that they won't. What's the same about these two? We're concerned with one event, Vikings making the playoffs. Now, odds ratio is different because in this case, we're talking about two events. It's the odds of one thing happening, one event, compared to the odds of a different thing happening. So notice it's just the odds on top of another odds. It's just a different thing. Condition 1 versus condition 2. Let's bring this to life with a simple example. Let's say we have a jar. It's got 21 marbles. 6 are blue, 3 are green, 2 are red, and 10 are yellow. You want to know the probability that you're going to pull a green marble. How many green marbles are there? 3. There's 21 in the jar. So the probability of pulling a green marble is just 3 out of 21, which is 0.143. It's a p-value, so we always round it to 3. Now, if you want to know the probability of pulling a red marble, there are 2 red marbles. There are 21 in the jar. It's just 2 over 21, 0.095. We good with that? Pretty simple. Now, if we want to know the odds of pulling a green marble, that's just the probability of pulling a green compared to the probability of not pulling a green, which is pulling anything else. So the probability of pulling a green, we already calculated, it's 0.143. And the probability of not pulling a green is 1 minus that, everything else. So 0.143 over 0.847 is 0.166. Oftentimes in odds language, we use fractions instead. So we'll say, hey, the odds of pulling a green is 1 in 6 or 1 to 6. Good so far? If we want to know the odds of pulling a red, same thing. The probability of pulling a red compared to the probability of not pulling a red. So we've got 0.095 over 0.905, which is 0.103. You can either say the odds of pulling a red is 0.103 or 2 to 19. Good so far? Each of these are just one event. Now, the reason I did both is because for odds ratio, we need 2 events. What are the odds of pulling a green compared to the odds of pulling a red? So the odds of pulling a green compared to the odds of pulling a red are just the odds of green over the odds of red, 1.6. Now, 2 very important key points here. Key point 1, put the bigger odds on top. I'm going to say it again. Put the bigger odds on top. Why? Because if you get a number that's less than 1, really hard to interpret it that way. You can, but it's hard because here's how you interpret it. 1.6. That's your odds ratio. What that means is that the odds of getting a green marble is 1.6 times more likely. You are 1.6 times more likely to pull a green than you are to pull a red. What would happen if I swapped this and I did that? Okay, someone with a phone out, will you do that math for me, please?
0.62.
0.620. So the way that I would interpret this, like hard for me to do these, is that it's your 0.62 times less likely to pull a red than you are to pull a green. It's really hard to interpret that way. Put the more likely event on top. What does an odds ratio of 1 mean? Equally likely, because what would happen if the odds of pulling a green were 0.50 and the odds of pulling a red were 0.50? What would your odds ratio be? 1. So an odds ratio of 1 means you're equally likely to pull a red and a green. So 1.6 is you're 1.6 times more likely to pull a green than you are to pull a red marble. What about if the odds ratio were 2-1 or 4-2? Which one's bigger? So here's green, here's red. Which one's bigger? They're the same. Even if it was that, they're the same. The odds ratio is the same. You're still twice as likely to pull one event as you are the other. Questions at all about this? Yeah.
Just fundamentals of probability, but why can't I compare the probabilities directly? Like, why do I need to do the odds stuff?
Because the effect size of the predictors are in odds ratios. Yeah, yes. The reason I'm teaching you odds ratios is because when you get your coefficient table, normally, how do you determine the strength of a predictor and what it's gonna do? Beta. There are no betas. We're dealing with logits, not raw units, and we're gonna get odds ratios. So we have to be able to look at an odds ratio of 1.6 and be able to say, oh, for every 1 unit increase in this, you're 1.6 times more likely to whatever the outcome. That's why I'm teaching you odds ratios, not just for shits. Good question. Ready for by-the-way example? All right, here's our example. You're an organizational psychologist and you've been hired by a local restaurant. AJ, this one's for you, per our conversation yesterday. The head of HR is concerned about high turnover amongst their servers. Specifically, she's interested in figuring out what predicts whether a server will stay at the restaurant for another year or not. After speaking with managers, you think that the two best predictors will be number of overtime hours worked a week and the amount earned in tips each week. The restaurant has provided you with current information on tips, overtime hours, as well as each server's intent to return form. Help the HR manager best predict people's retention status. So you want to build a predictive model that demonstrates going forward, how can we predict whether people will stay or return before they turn in their intent to return form. Good so far? Now, I wanted to do this really quickly because what differences do you notice here in terms of modeling between multiple regression and binary logistic regression? The title. Good. Yes. When you are thinking about modeling and the modeling mindset, nothing is different. You are still looking at your data, visualizing it, checking your assumptions, specifying your first model, checking the model fit, running other models to compare it, and then interpreting your final model coefficients. It's no different. What's different is what those model fit statistics look like and what those coefficients look like. But the actual modeling process is no different because it's just a regression model with a different type of outcome and a different estimation method. So here's our data. How do overtime hours and tips impact a server's decision? So we have, you want to draw it, we have tips and hours to retention, just a simple main effect model. Here's our data. We have hours per week of overtime, tips made per week in US dollars, and then whether they're returning or not on their server's intent to return form. Yes or no. Cool. So first thing we're going to do is we're going to look at our data. We've got hours and tips. So we've got 69 people, no missing data. Average hours of overtime worked is 2.97. Average tips per week is $509. This average doesn't really help us a lot. One helpful thing to look at is, well, how many people said they were going and how many people said they were staying. Sometimes we call this a base rate. This is like the base, what people are doing. So to do that, I find it helpful to run frequency counts. So I just added frequency in my descriptives, and you can see 36 people said that they were staying and 33 people said that they were not returning. So 36 people said they were coming back. 33 people said they were not coming back, 52.17%. You see, by the way, that matches that mean. That's because if you average zeros and ones like it's a number, you're going to get that average. So there's our frequency, our base rate in our observed data. This would be like if we didn't predict anything, this would be your guess. It's kind of like your mean of your outcome. It's the version of your mean of your outcome. All right, so now let's think of what probability odds and odds ratios mean in the context of this. So this is what we're working with as our observed data. It's all we have to go on. Without any predictors like tips and hours, this is what's happening with those 69 people. So the probability that I reach into the pool and that random person I select will stay is 36 out of 69. That probability is 0.522. Probability that I reach in and a random person will leave is 33 out of 69, 0.478. We good with that? The odds that a random worker will stay is 0.52 over 0.48. So that's the probability that they'll stay compared to the probability that they will not stay. And then the odds a random worker will stay, leave, thank you, is 0.48. So the probability they'll leave compared to the probability that they will not leave. If I want to know the odds ratio, I've got 1.09 and 0.917. I'm going to stack them on top of each other and I end up with 1.19. So a randomly selected person is 1.19 times more likely to stay than leave. Why is that important? Because I would like to figure out what predictors are going to drive that higher. What would make them even more likely to stay than leave? That's where the odds ratio comes in. But this is what I'm working with base rate. You look confused.
So this is a range of odds ratio.
Well, this is the odds ratio based on the observed data.
Oh.
I'm trying to build a predictive model that if I know somebody's tips and hours, that I can better predict whether people will stay or go. This is observed. This is based on observed data. So we're going to visualize our data, but we're not visualizing it with linear lines. We're visualizing it with natural sigmoid curves, natural log of odds. And it looks like, what does it look like? You tell me. 0 is not staying. 1 is staying. What does it look like is happening?
People that get more overtime hours stay more.
People that get more overtime hours are more likely to stay than people who get fewer overtime hours. And people who make more tips are more likely to stay than people who make fewer tips. We're going to check assumptions, but some of them don't apply because we're not using a general linear model here. This is not under the general linear model. It's not a regression, ordinary least squares. So multivariate normality, linearity, and homoscedasticity don't apply. Nothing about normality applies. What does apply is independent of observations, meaning my answers to my questions shouldn't affect Hannah's if she's also in the data set. And we don't want our predictors to be too collinear. Now, you would expect some relationship between tips and hours. If you work more overtime hours, then I would expect you to make more money in tips. But there's still other things that impact how much tip you make. So we can see, yep, there's a correlation between tips and hours, but it's not wild. And just like we can in linear regression, we can ask for tolerance and VIF of these two predictors when we run our model. But I'm not super concerned because we only have 2 predictors, so I already know what the tolerance is. If I want to know how much variance in hours is explained by tips, what do? Cry? No, what do?
Square it.
Just square that. That's my R. Just square it. It's fine. The tolerance is fine. Great. So I'm going to specify and run my first model. I'm going to start by running hours of overtime. Why? Well, I took a look at this and it looks like tips are more spread here. Do you see that? This is very clear, more hours of overtime, but it doesn't really matter. I'm going to run all combinations. So you could just pick which one you want to run. So I'm going to start with a simple binary logistic regression model with intent to stay regressed onto hours of overtime. So it's like a simple regression. It's just a simple binary logistic regression. What's the first thing I'm going to do after I run it? What would you do if this were a simple regression model? Don't lose your modeling knowledge. You know how to model. You specify a model. Then what do you do next? Hello?
Hypothesis.
No. What?
Hypothesis.
Not yet.
Assumptions.
No, we did that already. Thank
Wrong.
you. Model fit.
Yeah.
We're going to look at whether the model fits the data. Good morning, everybody. We're going to look at whether the model fits the data. And then we're going to look at the coefficients. And then we're going to run other models and see if the model fits the data significantly better. Remember I said, don't lose what you know how to do. It's the same modeling process as regression. So we're going to check the model fit. I'm really scared to go to the next slide because I feel like I'm going to blow your brains. The model fit looks different. Are you ready? Can we handle it? We can do it. Tasha's like, I'm ready. Now, in linear regression, regular regression, we compare our model to a model with no predictors. That's this beautiful thing here. We like our R squared, but then we also compare it to a model with no predictors. Yes? The same thing happens in a bilow ray model, but it looks very different. Don't worry, I'm going to walk us through this. This is the model fit table for binary logistic regression. This is the first part I want you to look at because it is completely analogous to what I just highlighted in yellow above. It is saying, does your model predict the outcome better than a model with no predictors? What is the model with no predictors? We looked at it. It's just, but there's no such thing as a mean because we just have stay or go. It's the base classification that we started with. So does your model predict better than a model with no predictors? Now I'm going to go through each of these pieces. So what is a null model? What is a model with no predictors? In regression, linear regression, I'm just comparing it back to what we know. In linear regression, a null model is a model with no predictors, meaning just the intercept. It's the same as the mean of your outcome. So if you think about linear regression, you have y equals b sub 0 plus b1 x1 plus b2 x2. A model with no predictors is just the intercept, meaning the average of y. You can get it from your descriptives. That's what that F stat is comparing in linear regression. In binary logistic regression, it's also a model with no predictors. It's also an intercept-only model. It's the sample classification rate. It's the actual classification rate that you had in your sample. We looked at it. 39 people out of 69 were going to stay, and 33 were going to go. Here it is. The accuracy is 0.478. Do you remember that? That was that 0.478 statistic. However, it's also given a chi-square value. Everything in binary logistic regression follows a chi-square distribution. That's why you keep seeing chi-squares. That's it. That's all you have to know because we're dealing with binary outcomes. Everything follows a different distribution than what you're used to. Instead of an F, it follows a chi-square. So the null model in this case, bless you, is a chi-square of 68 because we had 69 people to begin with. And the chi-square for the model with no predictors was 95.52. Now let's go back to that model fit. If you're lost now, don't disengage. I promise we're going to get through the model fit. This one's not easy to interpret this. So let's go to the full model fit. I'm going to go over each thing. So here's the intent to stay, regressed onto hours of overtime. Here's the model fit. I'm going to go through each piece. The first thing you have is deviance. What's the word deviance mean in English? Difference or bad, like how much you deviate from something, how far away from something you are. You can think about it that way. This number is the difference between what you got in your sample in terms of percent staying and leaving and what you expected based on your model. It's in units of chi-square. Everybody label that. Yeah.
This be comparable to error.
No, this would be comparable to like, yes, it would be comparable to error, but it's helpful as a fit statistic. Yes. So this is like this is in chi-square units. Then you've got this, which is the difference between your model's deviance and the null model's deviance. And the last thing you have is this R squared MCF called R squared McFadden. Oh, sorry. Here's your degrees of freedom. Before I get to the R squared, here's an interesting way to put it together. Here is the deviance of your model, 67.38. Here is the difference between your model and the null model in orange. Those two things together equal the chi-square of the null model. So this is the model, this is the chi-square of the model with no predictors. This is your chi-square, and this is the difference between your chi-square and null chi-square. So your chi-square in purple, that's why we use it as like a stat. Your chi-square in purple, how close did you get to actually predicting? So M asked if you could think of the purple as error. Yes, but that's our most helpful fit statistic. How good is your model at predicting what actually happened? That's what purple is. Orange is how much better is your model at predicting than a model with nothing. And when you put those together, you get the actual predictive power of a model with nothing. The last thing is what's called McFadden's pseudo R squared. This is it's like an R squared, but you can't interpret it like we do in linear regression. So it's not percent of variance. Why? Because there's no variance. The outcomes are stay or leave. So generally, if you have a pseudo R squared of like 0.2 to 0.4, that's good fit. Okay, I wrote that in the note. But generally, we're looking at whether your model fits significantly better. And then we're also looking at one other, what I think is more like lay interpretably helpful, which is the classification table. This one is more intuitive. This is what actually happened. So these are people who stayed, and these are people who left. Or sorry, these are people who left, and these are people who said they were staying. And these are people the model classified as leaving and classified as staying. So the model said of the 33 people that said they were leaving, the model got 28 of them and 5 of them wrong. You see that? Of the 39 people that were staying, it got 5 of them wrong and 31 of them, or 36, sorry, 5 of them wrong and 31 of them. So the classification success for each type is listed here. And you can also get the overall classification success rate of this model is 86%. So it classified all cases correctly 86% of the time. Meaning once we gave it its hours of overtime, it correctly classified 86% of the time. So how on earth do I report on this significance? This is all just model fit. How do I summarize my model fit? Well, look at the orange for a second. Does a model with hours of overtime predict better than a model with nothing?
Yeah.
Yes. Again, yeah, it's a chi-square instead of an F, but it's not different from what you already know. What's the overall classification success of my model? 86%. Here are your 2 options for how you report. Maybe. Here's option 1. The model with hours of overtime predicting turnover was statistically significant. Chi-square 67, 67.40, P less than 0.001. The model had an overall classification success rate of 86%. In this first example, I'm reporting my model chi-square. That's my model chi-square in purple. The second option is the model with hours of overtime predicting turnover fit significantly better than the no model. Chi-square 1, 28.14. The model had an overall classification success rate of 86%. Option 2, I'm reporting the difference between my model and the no model. Either is fine. Where did I get my degrees of freedom for this? You can see it on the previous slide, but it's sample size minus number of predictors minus 1. So 69 minus 1 predictor minus 1. Yes.
The classification success rate of the null model be 50-50 or
No, in this case, it's just the observed data.
what's the classification success rate of the null model?
The observed data. So it's 48.52.
Oh,
Yeah. Yep.
How do we report like McFadden's? Would we just say like?
Don't. These are your 2 options.
Oh.
Yep. Yep. Because it's N minus K minus 1. So you have 69 people, 1 predictor, and then minus 1. Yep. So not both of these to report model fit. So remember, you have the best way to mark this up is your model chi-square. That's that first one. Purple equals your model chi-square. Orange is difference between your model chi-square and null chi-square. You can report either. Got it? That was fun. Now, you're going to like this part because it's easier. Now, that's this model with hours of overtime. Now we can run additional models and compare them. This part looks very similar to how we compare models with multiple regression. Here's another model. This model is just predicting intent to stay just from tips. What do we notice? Chi-square difference is bigger, but what's our deviance? It's less than this deviance. What does that mean? Nope, we got to get this deviance down, guys. Our model, chi-square, you guys, we did chi-square before. So chi-square is the difference between observed means what? Our data. And expected. What does expected mean? Model. Anytime we're running a chi-square, we're looking at the difference between what we observe in our data versus what we expect in our model. This measure of deviance is the difference between what we observed in our data and what we expected based on this model. So do we want that deviance to be big or small? Small. So the model with hours of overtime, our deviance was 67 something. And when we look at the model with tips, our deviance is 58. Which model do we like better? Tips, exactly. But do we ever just look at numbers and say, yeah, we like that one more? No, but they're both good models. So what do you want to do next? So can we compare these to each other with a significance test? They're not nested, just like regression, nothing different. But what would you do if these were, they're just regular regression models, guys. We're just predicting a different kind of outcome. You have one good predictor and another good predictor. What do you want to do? Put them together. Good, let's do that. But we're gonna say, hey, a model with overtime was significant. A model with tips was significant. Cool, let's run another one. So we're gonna start with hours. Let's add in hours and tips. Looks just like it does when we run a regular model, except we're talking deviance. So here's the deviance. So remember, deviance is a chi-square, and it's the difference between observed and expected. What happened to the deviance when we added both in? Way down. But just like we significance compare, we're going to do a model comparison. Is a model with hours and tips significantly better than a model with just hours? Yes, there's a significant difference in deviance reduction, and that's significant. And here's our predictive accuracy. Here's our classification success. Model 1, 86%. Model 2, 87%. How do we report on that? Just like you report on regression. A model with hours of overtime and tips predicting turnover fits significantly better than a model with just hours. Delta chi-square 1. 22.1, p less than 0.001. The model with tips and hours had an overall classification success rate of 87% compared to the model with only hours, which classified correctly 86% of the time. Yes.
What are some reasons if we have less deviance, but also less predictive accuracy?
There are a lot of reasons that can happen. Yeah. I'm not gonna get into it now, but there are a lot of reasons. Your classification success rate can still, so here's the short answer to that. Your deviance, remember that what we're predicting is a logit, which is a continuous value. So your chi-square deviance value is predicting continuously. So the deviance is the amount of error that exists between those continuous values. Your classification is forcing a binary choice. And so sometimes the forced binary choice will be off. And so you can see a lower classification rate even when the deviance looks better. Does that make sense? And you can, we'll get there, but you can change the cutoff for that forced choice if you want. Yep.
Also, the model adds up to 95 plus chi-square.
Yes. Yep. Exactly. Because this is your model. The deviance is your model, and this is the difference between your model and the null model. Yep.
If that's the case, why do we even need to why does it even output the difference between the two models?
Because that's the significance test that happens. That's what's being tested from a significance perspective.
And you want that as high as possible.
Yeah,
Okay.
but that's where we're getting our p-value from.
Oh, where no one will be there.
So here's our final model. Okay, go ahead.
Say, is the P or is the significance test related to the accuracy level?
No, that's what I was saying to, remember that when we think about y equals tips plus hours, but we're predicting logits, the deviance is using this, as in predicted and expected logit. Classification rate is forcing a choice. So yes, they're related, but they're not exactly aligned. You can get a better deviance and still have a slightly lower classification.
Would you get a fully insignificant model with a really high?
No, they'll go in line with each other. Yeah. But for example, here's a good example. You see it here. So tips has a higher deviance, meaning it's got less error between observed and expected, but its classification is lower. Yeah. So let's look at the coefficient. Now you'll be like, oh, this is why I needed to teach you odds ratios. Let's start with the intercept. What is the intercept in robot form? So the predicted value of y, hello, when all predictors are 0. We haven't centered anything. Oh yeah, we did, sorry. Yep. When all predictors are average. Good, only because we centered, otherwise it would be 0. Now, but what's the very important thing to remember here? Are we predicting raw y values? No, what did we convert? We're predicting what? Logits. That's the really important thing to understand in binary logistic regression. We have converted the left side of our equation, the outcome, into natural log of odds so that it's continuous to match our side of the equation, which is continuous with tips and hours. So when hours and tips are 0, we would predict somebody to have 0.17 logit. Yes, that means nothing, which is why I'm never going to ask you to interpret that. How do we interpret the coefficient? This is the predicted logit for someone who works an average number of hours and makes an average number of tips. How do we interpret that? You know how to interpret this. For every 1 hour more worked per week,
Logit will increase by 2.5.
the logit will increase by 2.54, holding tips constant. This is not a moderation. You don't have to hold it average, just constant. Good. For every 1 unit increase in hours, every 1 more hour a week, holding tips constant, we'd expect a logit increase of 2.54. The point is, it's not working any different than regression. The only difference is we've converted our outcome into this continuous measure that is a natural log of odds. What is really important and what is interpretable are Z and odds ratios. Those are the 2 things that you're going to want to pay attention to. This is why I taught you odds ratios. Let's look at this one. 12.63, okay? Here's how we interpret that. For every 1 unit increase in hours, so every 1 more hour worked per week, someone is 12.63 times more likely to stay compared to leaving. This is like an effect size, sort of. It's like akin to an effect size. And then tips, how do we interpret the tip one? For every $1 more that people make, they are 1.03 times more likely to stay. Now, critical point. Everybody put your eyes here because people mess this up all the time. So, which one is the stronger predictor of staying? What's your instinct want to say? Hours. Why does your instinct want to say that? Well, because you've got 12.63 times more likely and you've got 1.03 times more likely. But what is true about these odds ratios that are not true about betas? They're unstandardized. Ready? We said for every 1 more hour worked. And then we said for every $1 more. If you work another hour, do you make more than $1 more? Usually, hopefully. So these odds ratios are really helpful, but they don't tell us which one is stronger. Where can we see which one's stronger? The Z, exactly. So here are our Z scores. The further out a Z or a T score is, the more extreme, the more further away it is from nothing, from 0. So this tells us what the stronger predictor. What's the strongest predictor in this model? Tips. Because it makes sense. Think about it. Now this is for every $1 more. Blow that up. For every $100 more, you're 100.2 times more likely to stay. Oops, now all of a sudden it looks like a way bigger predictor.
Yes.
The other way does too, yeah.
You could say for every $12 earned, you're getting an equivalent increase in probability. Like, is it easier to earn $12 more or is it easier to work 1 more hour?
Yeah, so they both matter. The moral of the story is they both matter. A model with both is better at predicting than a model with either one on their own. Although, to be fair, we didn't test the other way. But they both matter. They're both significant predictors. Tips is the stronger predictor, but not by much. You can't really use these to do anything other than get a logit. So it's not helpful to predict or not helpful to interpret, but what is helpful is to interpret the odds ratio and to interpret the Z. So the last thing I want to close with is, well, then what the hell is the logit helpful for? And it is helpful for something. Do you remember this slide where I took us from probability to odds to logits? Well, we can do the same thing back up. So check this out. An HR manager is worried that she's gonna lose her favorite waitress, Trudy. Given that, Trudy works 7 hours of overtime a week and makes about $100 in tips. What would you tell the HR manager about the probability of Trudy staying for another year? Well, you can just plug it in to the equation. 0.17 plus 2.54, her hours and her tips. Remember, we used a centered equation, so you got to use her centered scores. And what you get is this very uninterpretable logit, negative 0.23. But you can convert a logit back to probability. Now, do you have to do that by hand? No. You can ask R to do it. We're not going to do the math under the hood for that. You can convert logits back into odds, 0.79, and you can convert odds back into probability. Based on the number of hours she works in a week and the amount of tips she makes, the probability of her staying another year is 0.44. You better figure out a way to help her make some more hours or some more tips, because now she's more likely to leave than she is to stay. So the logits on their own aren't helpful, but you can convert logits back into probabilities. Yeah, we're going to do it under the in R. Cool. That's it. We have a lot of announcements that are very, very important. The first one is you have a binary logistic regression DA that is due on Tuesday. So we have demo on Thursday, it's due on Tuesday. No extensions on that DA. The number of extensions for the moderation DA was wild, especially given the number of days we had and when we did the code. I get lives. The reason we can't do it on Tuesday is because the exam is Thursday and the TAs have to release the key. They can't release the key unless it's turned in. So no extensions on Tuesdays, just that exception. It's got to be in on Tuesday morning. That's the first announcement. Second announcement, I think everyone's seen this, but the groups for DA for project have been up for a while. They're on Canvas along with sample presentations, sample papers, overview document, rubrics, maybe other things you might want, how to write a good research question, other things. Other announcements. Raider.
Yes, the DA for DA.
Oh, yeah.
Is due Thursday, so.
You gotta talk a lot louder than that.
Sorry, DA resubmit for DA 1 or 2 for 308C.
Oh, yeah.
Is due on Thursday, so please take a look at your DA 1 or DA 2. If you have one that you want to resubmit for, gonna get that turned in.
Yeah,
And-
it's a good review for the exam if you need to resubmit a DA.
And then office hours are virtual today. It's
Cool.
just an announcement by the Canvas.
Good. We are gonna pick up on Thursday with the demo. So, take today and tomorrow to do two things. One, review a little bit of what we did today in lecture. And two, if you have the opportunity, practice another moderation. There's gonna be a check-in on Thursday, for those of you who like to know that. I'll see you Thursday.
Wait, I have a question. You sent an email saying that our project name and manager is due today. I thought it's due on Thursday.
Do Thursday. Oh, that's fine if you turn it in Thursday. That's okay. Please download it so that you're not focusing on installing packages while I start demoing. And that's just a good reminder about R in general, which is if you are working on your own R while I'm lecturing or demoing and you run into an R glitch, let it go, fix it later. Just watch me demo and take notes. Because if you're focusing on trying to fix the R glitch, you're losing the notes on the demo that you're going to need later for the DA. So don't use the demo time as our troubleshooting time. Do that afterwards. And then the second announcement is, believe it or not, C is over next week. There's a final. I know. This is sort of that time of year where everybody's energy kind of goes like this. But it needs to not, because you have a final next week. And we start D. One more week to keep it together, all of us, myself included, and then we get a break. By break, I mean planning for everything that comes after break. But the link for exam review questions is up. It is easy, it's just 308C exam 2. Is the tiny URL. I will also have one of the TAs post it as an announcement on Canvas. Questions are due by Sunday. Whatever your end of Sunday is, which is likely later than my end of Sunday. And then I will finalize what I've already started on Monday. We will be going over all of the check-in questions on Monday, so you don't, similar to the midterm, you don't need to put any of the check-in questions from today in that review survey, because I'm gonna go over them all anyway. Does that make sense? Clear? All right, any questions before we dive back into content? Questions from online? Thanks, AJ. All right. Before we dive back into content, I want to make a note about BiLo-Ray, which is that we are admittedly and purposefully not diving as deep mathematically or under the hood into BiLo-Ray as we do into all of the other types of regression, like simple and multiple and moderation and mediation, which we will. That's on purpose, right? Binary logistic regression is an important tool to have in your toolkit in terms of being able to run that data in the case that you have a binary outcome. However, it's not wildly common, right? And there are not a ton of other analyses that build on BiLo-Ray in the way that everything builds on regression, right? So it is not like you need to go out and go 10 times deeper than what we've covered in lecture on BiLo-Ray, right? Where the level we hit in lecture is a good level. And especially as we prep, as we get ready for the exam, it's not BiLo-Ray heavy. Yes, BiLo-Ray is on it, but if you think about prioritization, that is not going to be the most important compared to all things regression, moderation, etc. Questions about that? I just know that a lot of people were like, but what underneath? Like, how does this work? And I love that, and I'm happy to entertain those questions. Like I will. I went crazy on like -2 log likelihood equations with a couple people after class on Tuesday, but don't worry too much if that's feeling like a lot. Cool. So plan for today. We're pretty like we're flex on time in the sense that I am sharing. I don't want to share. Stop sharing. There we go. We're flex on time in the sense that we only have the demo to cover and then we have the check-in. So we should have time to finish all of the check-in in class today, which is what I hoped. I'm going to start with the demo, but before we start with the demo, I'm going to pull up this is the deck. I'm going to pull up the deck and I want to take any questions that people have about BiLo-Ray before we go to the demo component. So I'll give everyone a second to just get their stuff out, orient to BiLo-Ray, and generate for yourself any review questions you might have about either model fit or coefficient interpretation. So let's stay in the deck just for a few more minutes before we then go to the demo component. Questions? Yes.
The Z-score in the coefficient table is just to compare predictor. There's really no use to interpret it. There's no deeper interpretation than that.
So there's two purposes of the Z-score. What does the Z always signal to you? So careful. Oh, good. I'm glad I asked that question. This is not a Z-score. This is not a Z-score. This is a Z-test, like a T-test, right? These go together. This is a hypothesis test, guys. It's just using the Z distribution. You've got a Z calc. And that Z is what's determining, right, whether the predictor is significant or not. Just like the T is determining. The T, by the way, we don't use the T to determine strength of predictor in a multiple regression, but we could. Do you notice that the strongest beta is also the strongest T? Because if you think about a null hypothesis test, here's the null hypothesis. Here's nothing. If you have a predictor with a very small effect, where is its T or Z score going to be relative to the null? Let's say here, right? Here's its T or Z calc. What happens if you have a super strong predictor way over here? That's how they work. That's the like match between strength of the predictor and strength of the T or the Z stat. Right? The stronger an effect, this is 308 basic, right? The stronger an effect you have, the bigger your test statistic. What is a test statistic? Always a ratio of. T or Z is a ratio of what? Effect over error, right? So when your effect is huge, a really strong predictor, that moves the T and the Z further out, away from the null hypothesis. So in this case, because odds ratio is unstandardized, we can't use it to determine strength. In a multiple regression, beta is standardized, so we can. So we don't have to use a T, but we could use the T in a multiple regression. We just don't. We don't have to. Here, we have to use the Z, the test statistic. But this is the test statistic. It's not a standardized Z-score. Does that help clarify? Cool, good question. Yeah.
Why do we run it on the intercept? Like, can you interpret that Z calc of the intercept, or is that just there?
Not really. It's the, I mean, it means that intercept is what? What's the null hypothesis? This is a great one. This applies to both multiple regression, simple regression, phyllo array moderation. What is the null hypothesis always of this test? Whether it's a T or a Z. First of all, what is it testing? What's the effect? It's always effect versus error, right? We have effect and we have error. Where in this coefficient table is effect? Yeah, it's your coefficients. B, where's your error? Standard error. That's your test. So it is always, no matter what, it is always testing. Gotta know this part, that the B, the coefficient, you can always just say coefficient because it's a coefficient here, even though it's in logit units. It's still a coefficient of your equation. It's a coefficient in multiple regression. The null hypothesis is that B is equal to 0. What is that then telling you for the intercept? It's telling you the intercept is not 0. If it's significant, in this case, it's not significant. So you'd say, hey, that intercept is not significantly different than 0.
Because it's
Because it's not significant. Yeah. Remember that this is in logit units. So it's not significantly different from 0 logits. That's the predicted logit for somebody with average hours and average tips. The predicted logit for somebody with average hours and average tips is not significantly different from 0 logits, whatever the hell that means. Yeah. Good. Other questions?
I have one.
Yeah.
Could you please go over the difference between with the model fit slide, deviation versus, sorry, deviance versus the other x squared? Just talk about the difference between those two real quick.
Yep. Let's look at this right here. The first thing that you can do right here is that you can, this is what R spits out to you, but you should note that this is a chi-square. That's the first thing that everybody needs to know. This is a chi-square, okay? So you have 2 chi-squares that you need to understand. And you can report on either of them to report the fit of your model. This is the chi-square of your model. This is essentially comparing your model to the data. Really underneath the hood, it's the -2 log likelihood difference between your model and a saturated model. Anybody want to calculate that? Didn't think so. So there's the chi-square of your model, and the degrees of freedom for your model is the number of people you have in your sample minus the number of predictors you're working with minus the one you always lose in degrees of freedom. So the way we do this would be chi-square 67 equals 67.38. That's the chi-square of your model. Cool with that part? Yeah. So remember that chi-square is always measuring conceptually way up here, guys. Chi-square is always measuring the difference between what you expect via a model and what you observe via relationships or saturation. So this is measuring the difference between what you predicted in the model using hours of overtime and what you actually have in the data from a probability perspective. Now, the second chi-square you have is actually, I like to think of it as like a delta chi-square. Because this is the difference between your chi-square, which is what? What's your chi-square? 67.38, and the null model chi-square, and the null model chi-square. So if you take this difference and this, you get the null model chi-square. Yeah. Now, in terms of reporting, first of all, why is the degrees of freedom difference 1?
Because there are only 2 things that you're looking at.
Yeah, there's only one difference, right? Here you've got, well, the difference between them is 1. Because in the null model, you have no predictors. And in this model, you have 1 predictor. So the difference between those is 1. Now, if you're reporting, when you're reporting, you can report on either. You can report on your chi-square along with the classification rate, or you can report on the difference between your model and the null model and the classification rate. Does that help, Ellen?
Yes, thank you.
Yep, good.
Jess,
Yes.
could you just then while we're on this slide, could you just go over again then how do we interpret like the classification rate data, like what the numbers mean?
Yep. So you get two different types of classification rates. You get one overall. So what that means is like, let's say everybody in class is my sample. Like, right, I take a new sample of people and I'm looking at, remember that my model is predicting your intent to stay from hours of overtime. What I do is I collect all of the hours of overtime from all of you. And then using my model, I classify you as either staying or leaving. The overall classification success rate says I'm going to be right 86% of the time. And 14% of the time I'm going to be wrong. So for some of you, I'm going to say, yeah, they're staying another year. When in fact, when you turn in your intent to return form, you're being like, nah, I'm gonna leave. We also can see the breakdown for which I classified correctly or not. Sometimes you'll see that models are better at classifying one of the outcomes than not. Maybe I do a better job. In this case, I'm slightly better at this, but probably because I have more people there, right? But sometimes that's not always the case. Sometimes you can have a model, right? And you can think about that from a logical perspective. Like there are certain predictors where as soon as somebody like is high, it's a guarantee they're coming back. But when they're low, it's like, no, they couldn't. So that might make us predict people coming back a lot better, but be more wrong about the other one. You don't always see an even or equal classification success rate across the two observed outcomes. Yeah.
When you report that, do you talk about that kind of like how we do in multiple regression, where you could say it works better for X?
If it's interesting. So if I got like, normally I would just say, this is my classification success rate. And then I would look at my predictors, right? And talk about those individually. But if for some reason these were wildly different, that would be worth commenting on. But otherwise, they're roughly the same here, right? They're folding in together to an overall classification success rate that's pretty representative of both outcomes. Got it. Yeah, good question. Good. Other questions?
I've got one. This is maybe a little bit theoretical, but going back to the coefficient regression table and the z-test for the different coefficients, what is it about binary logistic regression that lets us use a z-test in particular for this test, as opposed, because don't you need like the population mean to be able to do a z-test?
My hunch is that it's probability, that we're dealing with probability, but I don't know. I have to look it up why it's a z and not a t. Yeah, but my hunch is that it has to do with we're predicting probability.
Yeah, it's more theoretically.
You would have theoretically normal distribution.
Yeah, that makes sense to me. Thanks.
Yes.
So can you help me explain when it says like the deviance chi-squared is 95.52? How do I explain that to somebody? Is that necessary for me to explain that? I should ask that first.
Yeah, that's a good question. 95.52. Like the null model. Let's hold on that. Yeah, I'm gonna hold on that for now till we can do the prioritized stuff. And then if we can get into that, we can get into that. For now, as long as you understand that a null model is no predictors, just the classification rate we start with, that's fine. Yeah.
Are we going over assumption and checking in the demo?
We did, yes, but there are only two and they're pretty simple. What are they? What things are not gonna apply?
Independent observation.
No, independence of observation always applies. What's definitely not gonna apply assumption wise? Normality, because you don't have a continuous outcome that you're predicting. What else? Homoscedasticity. What else? Linearity. That's the whole premise behind why we have to use Bilot array is no line. So the two that do apply are independence of observations. And then what's the other problem you could still run into here? Yeah, you could still specify a model with two predictors that are too related to each other. So you can still have an issue of multicollinearity because the predictor side of things looks exactly the same as multiple regression. So those are the only two. But yeah, we'll look at it. Yeah, and you don't check those any differently than you would check them. Like, how do you check multicollinearity? Tolerance in VIF and the correlation table. Everything on the right side of the equation, the predictors, is exactly the same as regression. So we can still run correlations between the predictors. We can still ask for tolerance models between the predictors, VIF and tolerance. None of that changes. That looks exactly the same. It's only the outcome that's changed. Want a demo? Let's demo. I'm gonna start here. We're gonna go back and forth between slide and demo. So this is real data from the Michigan Employment Security Commission. So they offer this program in Michigan called JOBS. It stands for Job Opportunity and Basic Skills. And it's a program that helps promote reemployment of individuals who lose their job and prevents sort of the negative effects of unemployment on mental health and well-being. So this is their big 95 study, and then there's another repeat of it, which is the data we're looking at. So in the 95 study, the authors found that participating in the program not only facilitates reemployment, but it also reduced depression symptoms at time 2. So they collected depression data at time 1 and depression data at time 2. And they found that participation in the program reduced depression at time 2 while controlling for depression at time 1. So 2 years later, they were like, great, participating in the program works, but why? They were like, let's actually collect data on the psychological processes that drive that reemployment. So it's not just like you show up in the door and automatically it works, right? What about participating in the program drives reemployment? So in this study, they recruited about 1,800 respondents, and then they ran screeners, and between that and dropouts, they had about a little over 1,000 participants to retain for analysis. So all participants had been unemployed for at least 13 weeks. They were still seeking a job and were not expecting to retire within the next 2 years or be recalled back to their former jobs when they entered the program. Good. So here are the variables that we're going to look at. Treat, which is short for treatment, is participation in the program. So it's a binary variable. You either participated or you didn't. Economic hardship is an individual's level of economic hardship when they entered the program. Depress is time 2 depression symptoms, so depression following completion of the program. Mastery is this kind of combo variable that has to do with things they build psychologically in the program. So it's a combination of job seeking self-efficacy. So how much do you now believe you can find a job? Locus of control. How much is finding a job within your control? And self-esteem. The idea is participating in the program ideally works by raising these 3 things, and they combined them into this thing they called mastery. I don't know why they did that. I would have kept them separate, but they did, so that's what we're working with, mastery. And then we've got a bunch of demographics: sex, age, occupation, marital status, race, education, and income. And then finally, we have our outcome, which is employed, right? So it's a dichotomous or binary variable that indicates their employment status 6 months following the intervention. So 6 months after participating in this program, did they have a job or not? Okay. Questions at all about the variables? So we're going to take a little bit of a different approach here in the sense that rather than hypothesizing, I think it's this and this, we're going to play in a more exploratory way. So one of the ways that you can play in an exploratory way we've done before is build up models starting with one thing. But we can't run a correlation table here, right? Between outcomes and predictors, because we've got a binary predictor. So I'm going to go the other way. We're going to run a saturated model first. So a saturated model is a model with everything we've got, and then we're going to make some judicious decisions along the way about what we might want to retain in the model and what we might want to take out. This is never how you would like write a manuscript or an article, right? Usually you're lit reviewing and prioritizing, but we're not going to lit review right now because we don't have time for that. All right, so here's our first model that we're going to use. We've got treatment, it's binary, got economic hardship, continuous. Mastery is continuous. Depression at time 2 is continuous. Sex is binary in this study. Race is binary. So they took all race responses and they dummy coded them into white, non-white. And then you have age, which is continuous. Let's go to the demo. So we're going to read in the data, and then I'm going to change those titles, the column names to lower. You can see we have other data in here. So we've got marital status, education, income. We have job seeking self-efficacy as separate from mastery also, as well as inside mastery. There's a collinear problem that we would have. That's a good example, by the way. This is a collinearity problem that I have seen students do. running predictors where you run like predictor A and then predictor B, which is a composite that also contains predictor B. That is a recipe for multicollinearity waiting to happen. We also have in here, so treatment and employment have both been dummy coded already for us. So has race, so has sex. So we're going to use those. After we read in our data, the very first thing we need to do is get to know our data, visualize our data, prep our data, check assumptions. So we're going to run descriptives. Notice it's the same descriptives code we always run. The only thing I added here at the end, which is not something we normally add when we're using all continuous variables, is FREQ, frequency, equals true. What that's going to do is give us frequency counts for everything in our data. FYI, if you're ever writing a manuscript and you're trying to build your demographic table, right? Like how many people identified as this race, or how many women did I have in my study? How many non-binary? FREQ equals true is your friend, right? Because that is how you get all of the frequencies for all of the responses that you have in your survey. So we're going to run it and I'm going to open it because it's going to be fairly big. Let's see, Jason, moment of truth. Nope. See, today, no. You see that? No scroll today. Last week, yes. Today, no. Who knows? Jason was like, your R pop-out window scrolled. And I was like, it is. And now it won't again. No one has yet to figure this out. So here we have no missing data. We've got mean of economic hardship on a scale of 1 to 5. We've got age ranging from 16-year-old to 76-year-olds with an average of 37. Yep, 37. We've got mastery. We're using mastery. So that ranges, interestingly, from 2 to 5. So we don't have any 1s in the mastery column. And then down here, we've got our frequencies, which I can't scroll. So I'm going to look here. So we've got frequency of sex. So you can see how this is super helpful for writing a demo table. If you need to write demographics up, right here are your demographics. What I want to look at is this. So we've got 400 people who didn't participate in the program who are in this study and 879 who did. And then this is the big one. So this is our outcome. So of the 1,200-ish people that responded in the survey after 6 months, 503 of them were still unemployed and 782 of them were employed. So that initially we've got 61%-ish, right, that were employed at the end of the 6 months period. Now I'm going to run a correlation table. What am I going to run a correlation table on and why? I'm going to run them on my predictors, not my outcome, but not all of my predictors, just my continuous predictors. Why am I going to run it? What's the purpose? Can you talk louder? Because otherwise our lovely friends online can't hear you.
See the relationships between the predictors to see if there's any overlapping areas explaining.
Perfect, right? We're going to look at the relationship between our predictors to see how much overlapping variance they have, which might then be overlapping variance, except in this case, not variance, but how much overlapping explanatory power they have in our outcome. I'm going to throw mastery in here too, and self-efficacy in here too, and let's see what happens. Oh, I didn't put it in there, but let's do it. I'm going to put it in there. 14. So here we have our correlation table. Nothing wild. And age is significant here, but the coefficient is really small. Why is that R so small and still significant? What's the explanation for that?
Minimal error.
Yes, but there's something causing that minimal error. Anybody remember my example of the gender discrimination in the organization from 308A? If I walk into an organization and the person says to me, we don't hire women here, I'm out, right? But otherwise, if I get subtle, how long does it take me before I realize there's gender discrimination? What explains this? It's the core concept in significance testing, guys. What concept represents the ability to find an effect that's there? I heard it from somebody. Power! Power is what drives finding an effect that's there. If the effect is huge, how do you get power? You don't need a lot of people. If the effect is really small, how do you find significance? Great. How many people are in this study? That's how. So that is driving down that error. That is mathematically, though, what that 1,200 is doing, is driving down that error. Because they're not spread all over the place. They're all kind of regressing to that average. Write down the word power on your notebook. And if that is still not clear. Let's make sure that that isn't a lasting concept from 3, please. That is huge. And then, remember I said that they made this mastery thing out of 4 other things, right? Locus of control, self-efficacy, and self-esteem. That's why it's so correlated with job-seeking self-efficacy, because job-seeking self-efficacy is in it. This would cause a collinearity issue, 80.80 correlation. That's pretty high. We're not going to use both because we understand that one is a composite including the other, so we wouldn't do that anyway. But my guess is if we ran them together, we would see tolerance issues. So now we're going to visualize our data. Normally we visualize our data with scatter plots, but the problem with scatter plots is that they are graphing what kind of relationship? Linear relationship. We need to graph sigmoid curves. We need to apply the natural log of odds. So we're going to use a different function here, which is a logistic plot. This function comes from that package that I asked you to install during warm-up. So if it's not running for you, it's because you haven't installed PopBio. If you haven't done it, just skip the graphs. You don't need them for anything else. Install PopBio later. Here's what they look like. It would be really nice if they labeled the axes. So our first one is economic hardship, kind of all over the place. So if you think down here, 0 is not employed and 1 is employed, probability of being employed. That's what's graphed on the y-axis. What do we notice here? Well, people's economic hardship level is all over the place, both when employed and when not employed. Here, however, this is mastery. What do we notice? What's true of people when mastery is higher?
Much more likely to get hired.
They're much more likely to be employed versus people who are lower are down here, right? Less likely. So at this point, visually, just like in a scatter plot, when we saw a really steep line, we'd be like, oh, that's a really strong predictor. This is giving us a hint that this is a strong predictor of employment. The next one is depressive symptoms. Couple interesting things here, right? What's interesting here is we've got a lot of low levels of depression at time 2. Here, we've got a little bit more spread. This is age, but these seems very equivalent. They're stacked right on top of each other. And then this is not a helpful thing, super helpful. This is treatment, not wildly helpful. So we're always going to center our continuous data so that we can interpret when things are average, not 0. So this is the same way we interpret or we center data everywhere else. Yeah. Say it again.
Is 0 for treatment only dropped out? What is 0?
No, 0 for treatment is people who didn't participate in the program. Yeah. So they recruited people who were unemployed at the beginning of the program, measured them 6 months later. Some participated, some didn't. So it's like treatment control group, but they measured the psychological constructs of both. Center our continuous data. I'm gonna end up at the end here. These are all now people's scores relative to their mean, just like it is in multiple regression. And then we're going to run our model. So the model code looks very, very similar in terms of format, but the function is different. So the function here is log red bin. So logistic regression binary, like bilo-ray, but it has less of a ring to it. Log reg bin, call it that. I don't like that. It's also from JMV. Start with your outcome, your data set, DAT. Your dependent variable is employee. You're going to list your covariates just like you always would. Your continuous ones, we're using the centered, the non-continuous, they're just their normal binary variables. Then we're going to run that saturated model first. So remember, we're going to start by running, where is it? Where are you? That guy first. And we're going to see what happens. Reference level is important. Okay, you have to indicate what your reference level is. So you can run a binary logistic regression without dummy coding your outcome. So for example, if my data said employed, not employed, I could leave it that way. And I would just tell my reference group is not employed. So I just have to tell it, because it doesn't know what a 0 and a 1 means. I just have to tell it, hey, I want you to keep this as the reference group so that when we interpret those odds ratios, right, for a 1 unit increase, you're however times more likely to what? Be employed or not be employed. You have to decide what the 1 is going to be and what the 0 is going to be. In this case, 0 is our reference group. It's not employed. Model test, that's the same. Do we want to compare models? Don't worry about AIC. It's another fit index, which we'll learn in D. OR is odds ratio. That's saying like, yes, we want to know the odds ratio of each predictor. Class is give me the classification table. Colon equals true. You know that one. That's our collinearity stats. And ACC equals true is the overall classification success rate of the model. Shall we run it? Here it is. Here's our model. Our chi-square of our model is 1012. The difference between the null model and our model is 708.21, and that's significantly different. Meaning our model, right, predicts or classifies, more specifically predicts the likelihood that someone will be employed significantly better than a model with no predictors. So knowing all these things about people gives us a better chance of predicting whether someone will be employed versus knowing nothing, okay? Because knowing nothing, what are we going to use? Just the base probability. We can look down at our collinearity stats. Here are the tolerance scores of all our predictors. They're super high. No collinearity is an issue here. They're all tolerant on their own. And then we have our coefficients. So remember that our actual estimates are B's. Those are still B's. We could write out the equation just like we do a regression equation. It would look identical. Y equals 0.51 plus 0.29 x1 plus, they're just coefficients, they're B's. But they're predicting Y in the unit of logits. So for every 1 unit increase in economic hardship, we would expect a 0.29 logit increase in Y, holding everything else constant. Not a helpful number for you. So they're helpful if you want to predict something, but they're not helpful for interpretation. What are the 3 things that are helpful for interpretation? The Z, the P, the odds ratio. Because the Z and the P tell you if this predictor matters or not, right? Because if the P value is not significant, it means that this coefficient is no different than what? 0, right? Don't forget that null hypothesis test. So the Z and the P collectively are telling you how strong is this predictor from nothing. It goes all the way from 0, which is no relationship between this predictor and the outcome. That's what happens when P is not significant, all the way to a really strong predictor. If you think about it like a null hypothesis curve, 0 is the smack dab middle of the null hypothesis. That's no effect. That's what we say it is when the P is not significant, when we retain the null hypothesis. From there, we can go as far out on the curve as we want to, based on how strong the predictor is. That's where we see in the Z. And then the odds ratio, we can interpret as a type of effect size, but in unstandardized units. So let's look at this. What is the strongest predictor? First of all, what are the predictors? Significant predictors of employment here. Economic hardship, depression at time 2, mastery, and that's it. Good. What's the strongest predictor? What evidence would you give to support that? The Z, not the odds ratio. Yes, the odds ratio is huge, but this is your evidence that it's the strongest predictor, right? It's way past your rejection region of your null hypothesis curve. It's way out there. In fact, you know what the Z, do you guys remember from through it? The Z, what's the Z crit? Was it 1.96? So anything more than 1.96, we're going to reject the null hypothesis. That's why that's not significant, and that's not significant, and that's not significant, and that's not significant, because they're lower than 1.96. It's like everything I tell you in A matters still. Crazy. How do we interpret this odds ratio? Times more likely. Yeah. So for every 1 unit increase in mastery, you are someone is 190.67 times more likely to be employed than not, right? Isn't that crazy? But think about why it's so big. How do we think mastery is measured? In fact, we know how mastery is measured. What was the scale? We looked in the descriptives. This is why you look at your descriptives, y'all. Go look at your descriptives. You have it in front of you.
Oh, it's kind of short, the range is.
Yeah. The range is small and it only goes from 1 to 5. So if you think about moving 1 point up in mastery on a scale of 1 to 5, that's a pretty meaningful increase in mastery. Yeah, like you've just upped your self-efficacy, your self-esteem, and your locus of control, like a 20th of the scale. Like it's only broken up, or a fifth, sorry, of the scale. 20% increase. That's a 1 point increase. That's a lot. So when that happens, you are 190 times more likely to be employed. Good. What about 1.33? For every 1 unit increase in economic hardship, you're 1.33 times more likely to be employed. Interesting that these are both positive, right? Now, we're going to take a break. And when we come back, we're going to make some decisions about what model to run next. Okay. By the way, here are the results. We're going to look at this when we come back and make some decisions about what to run. Let's come back at 10. Come back at 10, guys. Here was our results. I color-coded them by significance or not. And we have to make a decision as researchers, right? What we do next. So there's not a clear-cut answer here. What are some options for what we could do? Welcome back, everybody online. Let's go. Hold on. Thank you. Okay, yay. You can tell by looking at the screen, like who lives in warm climate. Like Tasia and Jess are wearing tank tops. And Annabelle's wearing a hoodie in Jersey. What are some options for what we could do here? Like what you would do as the next model? Yeah, Emily. We could run the model with just economic hardship, mastery, and depression. Good. Anybody not want to do that? JJ, why?
I think we should add
Why?
What's significance? It's possible that this or age and after that variance, so we'll see it when they're removed.
Awesome. So both are totally valid. So you could just run them with the significant predictors. But a good thing to remember is that each of these coefficients is the coefficient accounting for all the other coefficients. So whenever you remove something from a model, it will or could change the other coefficients. So I'm sort of, and I also like the demographics I feel a little less tied to, although I agree like race is close. The treatment one, I'm like, wait, participating in the program or not, it's close to significant, right? It's got a positive odds ratio, and shouldn't participating in the treatment like have an impact on employment? I don't feel ready to abandon that predictor yet. I may need to eventually, but for right now, I made the same decision that JJ just suggested, which is I said, let's cut, I don't want to give it away. Let's cut age and sex, which are very small coefficients. And in fact, look at the odds ratio here. It's even less likely. So let's run that. So my next model, oh, here I ran the no model for fun. There's the, by the way, there's the, there's the chi-square of the no model. So here's my second model. So I've got economic hardship, depression, and mastery. Those were our significant predictors in model 1. And then I left in race and treatment because they were close. Good, let's run it. All right. So my deviance in model 1 was 1012. My deviance in model 2 is 1014. Didn't actually go down. Chi-square 705. And let's look at our predictors. What do we see? Same exact pattern. So race and treatment, different p-values, but still not significant. Mastery still the strongest predictor, right? 14.48 as our p-value. Were they up here? Pretty similar. So now let's go here. This is what it looked like. Give it away. So here's what it looks like. So treatment, not significant. Economic hardship, mastery, depression, still significant. I still am weirded out by this treatment thing. I don't want to take it out yet because I'm like, shouldn't treatment predict employment? Like that's the whole concept here, right?
Especially if you work.
Yeah, especially if you work for this program. Right, so I'm gonna run one more model and just see. I'm gonna take out race. Okay, so just gonna run economic hardship, depression, mastery, and treatment. No, still no. Well, hold on. So here we go. Here's what it looked like. Yeah.
I might be skipping it.
Yeah, you
So,
might be. Economic hardship, mastery, and depression, significant. Treatment, not significant. So I think I can now go to Emily's idea, which is I think economic hardship, mastery, and depression are the three things that we've got working with. Yeah.
Patterns or squared was above 40, is that problematic?
Yep. No, they're good models. Yeah. So I think we can go with economic hardship, mastery, and depression. Now my question is, how do you want to run those? I just heard it. Who said that? Say that again.
The hierarchical model to it, add one at a time.
Good. We know that all three of them are significant, but let's actually run it with just mastery to start and then add in those other two and see if we can increase our predictive power. It's not variance, don't forget, but let's see if we can increase our predictive power here. So that's exactly what I'm going to do in this last set of models here. I'm going to start with mastery because that was my strongest Z-score. Then I'm going to go to depression and then economic hardship. And I'm going to compare those models. But
Why not run treatment first?
because I already know it's not significant inside those models.
One of the thing
You want to see it by itself?
By
Yeah,
itself.
that actually will reveal something.
Yeah.
Watch.
because
Yeah, just
What?
watch. Don't,
Okay.
just watch. Check that out. Treatment on its own does predict employment. Riddle me that, Batman. Treatment does predict employment, but now I don't want it in my models, so I'm gonna take it out. But I want us to remember that treatment on its own, but look at model 2, what happens as soon as I add mastery? Not significant anymore. Now, why? Hannah,
Because the,
louder.
because the treatment is teaching mastery.
That's exactly. So the idea is simply showing up at the treatment or not is not actually as important as whether you learned what you needed to learn out of the treatment. So it's essentially what we're measuring is both mastery, high levels of mastery, and participating in the treatment are indicators of treatment. One is a better indicator, which is not only did you show up, but you actually got a lot out of it. That's the mastery score. The other, basically, you can't, in some ways, they're multicollinear, but because one is binary, we're not getting a tolerance score for the two of them together. Yeah.
So like all categorical predictors were not significant, so is it better to use?
No, that just happens to be, that's not a feature of them being categorical at all. Yeah, it's a feature of what they were. Yeah, so race just is not predictive, age is not predictive, sex is not predictive, treatment was not predictive, but it was predictive. Do you understand? Like, that's the important thing to understand is by itself, it was predictive. Because the idea is if you are somebody who participated in the program, you are 1.45 times more likely to be employed, right? Than someone who didn't participate in the program. But when we add in a measure of mastery, which is not just participating, but also getting something out of the program, right? Then just participating doesn't become predictive on its own. Bijan. Nope. Probably not.
But if you were to measure the treatment based on like number of like classes they attend.
Uh-huh.
And then, reference that with BIF, we'd be able to.
You might, yeah. So if, yeah, good question. So he's basically saying if treatment were measured in a continuous way, could we then see in the tolerance and VIF scores that it's wildly related to mastery? Yeah, right? Here it's like we have to understand collinearity from a theoretical perspective because we can't actually calculate a tolerance score. Yeah. Yep. Yes.
We don't actually know for a fact that these people did not have mastery before the treatment. Is it possible that we don't draw that conclusion, but just say mastery is so important regardless of where they got the treatment or not, and that it's irrelevant?
Yes, although, that's a good question. Yeah, it would be better to have a baseline score to control for in here. So what you would want is, you would want to have inside this model, you would want to have mastery and also time 1 mastery. And even if time 1 mastery wasn't significant, you would leave it, right, as a control. So saying, regardless of where people started before the program. Yeah, exactly. So I want to see those three together though. Take treatment back out. That was a good thing done though. So here we go. So model 1 had just mastery. Model 2 had depression and mastery. And model 3 had depression, mastery, and economic hardship. What's our strongest model? All three. Model 2 is better than Model 1. Model 3 is better than Model 2. So here is our final model. What's our strongest predictor still? Mastery, right? What's interesting about depression and economic hardship?
They're both positive.
Yeah, that's interesting. But why is that? That's my assumption there is because it's considering mastery, right?
Yeah.
Like if you take two people with the same mastery level, then if I have more economic hardship, I'm actually more likely to go out and find a job.
So motivation.
Maybe. Well, we don't know why. You can't assume it's motivation. Could be my spouse is saying you need to go do that. Like, I don't know. Can't assume this. You can't assume that. Yeah, that's external motivation. Yeah, extrinsic motivation. You can't assume the psychological mechanism, but.
So would you say that whether you come in with a high level of mastery or you develop the mastery, I guess economic hardship may or may not change, you would have less depressive symptoms because you're like the locus of control?
No, you can't make that assumption. The only assumption you can make, the only conclusions you can draw here is that mastery, depression, and economic hardship all drive probability of being employed in a positive direction. However, mastery plays way more of a role in it than depression or economic hardship does. The depression one is interesting to me. Yeah. But here's what's kind of interesting is to Victor's point, we don't have depression at time 1 in here. So one thing I wonder is actually does it actually not become a significant predictor if you control for people's pre-depression symptoms?
So if you did change in depression?
Because we don't know their baseline.
Exactly.
Are you teasing it there just that employment may drive up depression or?
No, just that this is their depression at time 2, right? And we have no idea what their depression at time 1 is, so.
They could have had a really high baseline.
Exactly, so if they had a high baseline and it stayed high.
So I kind of cheated and looked at what was in the mastery scale.
Yeah.
And it's, what is it?
Locus of control.
Self-efficacy.
Yep.
And then
Self-esteem.
Yeah, and it's I think what's within mastery would be.
But offsets.
Yeah.
Yeah, it's a coping mechanism for depressive symptomatology. Yeah, totally. But what's interesting still is that depressive symptoms remains high or remains predictive. But what I'm saying is if people started with a high baseline, right? Then it just might be that those are the people who also ended up high in mastery, right? And so at the end, they still have high depressive symptomatology and that predicted employment, but it's only because they are the ones that happen to develop lots of mastery. If we controlled for time 1, that time 2 would potentially go away. The same is true for economic hardship. Yeah. What's the moral of this, the big picture finding here? If you're the program, it's not defund the program, it's what?
Develop mastery.
But even more than that. Does the program work? Yeah. And specifically, why does it? Remember why these people did this study two years later? The first study was just does the program predict employment? Then they were like, why? What are the psychological mechanisms? They answered that question.
Yeah.
The program works because it helps people increase their self-esteem, their locus of control, and their job-seeking self-efficacy. That's the highlight. Yeah.
So our study need to differentiate between those 3.
Yeah, they should have done that here. Yes, 100%. Yeah. Although my hunch is that if they combined all that at some stage in this data, they have it separated somewhere, and it might be a good thing to parse out. Yeah, good. So now, how do we use the model? So here's the only place really where logits become helpful. So this is our final model. There's our B sub 0. Our intercept, there's our B1, there's our B2, and there's our B3. So we can use that to predict the probability that somebody is employed. So here we have a person whose mastery is 4.3, their depressive symptomatology is 1.2, and their economic hardship is 2.8. We're gonna predict their score, but in what unit? Logit. So we're going to predict their logit using the normal regression equation we always do, just in logits. You have 2 ways to do it. Don't forget we did what to our continuous variables? We centered them, which means we can't plug these in. We have to plug in these minus the mean. So there's actually 3 ways that I could write this code. One way is I went to the descriptive. So here's the equation. Let's write the equation out together. Everybody do this. Equation. Y equals 0.72. That's the intercept. Plus 5.24 mastery. What's next? Plus 0.82 depression plus 0.27 econ. That's the equation. It's a normal, just like we write a regression equation, we just go straight down the coefficients. Now we need to plug in these values, but centered into the equation. One option, I don't recommend this, is to manually go to the descriptives, find the means, and subtract them. I went up to the descriptives, I found the mean of mastery, the mean of depression, and the mean of economic hardship, and I put them in manually. Why would I do that? I don't know. Much faster is just do their M score minus the mean of mastery, D minus the mean of depression, or E minus the mean of economic hardship. Here's a cool third option I just thought of, which I kind of like more. Center this person's values. There are their raw values. Let's make them centered. How do we do it? Well, same way. 4.3 minus the mean of dot mastery. So we could do this. And now what equation do we get to use? Super easy, right? We just plug them in. What did I do? So you see what I did here? I just centered their scores first by subtracting the mean, and then I plugged it into this equation. Are there questions about that? Yeah.
The very first, like, is it already loaded?
This, you don't put their raw, remember what we did when remember this? We didn't touch anything on we just translated probability, which is not continuous, into natural log of odds. So only the outcome is in natural log of odds. The predictors are all in their regular units. Yeah. So we're just putting in this person's score of this person got a 4.3 on mastery out of 5. The only thing we need to do is center it. Yeah, good clarification. So we took their raw scores, right? Feature of R, if you ever want to store a number as something, you just do, like, you could just do pizza. Now I would have to put pizza in here. You can name things however you want. So we took the original values, we centered them by subtracting the mean, and then we plugged them into the equation that you wrote. So remember, it's predicting a logit. Great, this person has a predicted logit of 2.41. Yay! What are we trying to actually predict? Concretely, what's our outcome? Whether or not they'll be employed. Does this tell you whether or not they'll be employed? No. But going back to that slide, we're down here in the red. We have their predicted natural log of odds, their predicted logit. So what do we need to do? We need to go back up. So we're going to take their logit and we're going to convert it into an odds. And then we can take that odds and we can turn it into a probability. And I promise you wouldn't do it by hand. You're not. So you can add, I don't have notes here, so you might want to add notes here. So this is converting logit, which is the natural log of odds, to odds. So if you look at here, the opposite of the natural log, and her odds are 11.09 to 1. There's a 1 underneath there, 11.09 to 1. Then we know that odds are probability of outcome A compared to probability of not outcome A. So we can create that formula. And let's look at all three together. So her logit, predicted logit is 2.41. The odds of her being employed are about 11 to 1, pretty high, right? And then the probability that she's employed with scores like what she has is 92% likely to be employed. That makes sense. Which of her scores is really high? Mastery. And we know that that's the #1 driver of being employed. That's it. That's all I got.